It's always a great pleasure to be back at EPFL. Thanks a lot, Pascal, for the invitation. Thanks for everyone for coming. So today I'd like to talk to you a little bit about some of my recent works at Google DeepMind, focusing specifically on using machine learning to discover algorithms, to discover new mathematics. So this is part of the science team in DeepMind. There is something called the science team, where you might have heard research outputs such as, for example, AlphaFold on the protein structure prediction part of things. So the science team is organized into initiatives. So we are working in math and computer science initiative, where our goal is to do precisely this, to discover new algorithms and new mathematical results. So our mission precisely is stated as follows. We want to discover new, verifiably correct and efficient algorithms for impactful problems using machine learning. So there is a few keywords here. First of all, verifiably correct. We want algorithms that work all the time, not just algorithms that perhaps work, perhaps they don't work. And we want to do so for impactful problems. So what we call in DeepMind root node problems. So problems such that if we unlock those, then we would be able to essentially unlock many other problems. Okay. So if we're successful in essentially using machine learning to design new algorithms and to discover new mathematical results, this can have huge implications, as you can imagine, because algorithms are used everywhere. So if we're able to essentially make algorithms more efficient, then this can have huge implications. Now, the problem is that it's an extremely hard problem, right? So there are a number of challenges. First of all, the first of them is essentially formulation. How can I even start formulating the problem of discovering a new algorithm for the task of, say, matrix multiplication, which we'll be considering today, right? So how is this even related to machine learning, right? So we'll see step by step a little bit through a use case, how we can take such a problem and then convert it into a machine learning problem, and why is machine learning the right tool for it. Now, even if we're able to formulate as a machine learning problem or as a game, as we'll see, there is the issue of scaling, right? So we will see that the kind of problems or the kind of problems that we'll be tackling have a huge combinatorial search space. So how do we navigate efficiently in this search space? And perhaps these challenges explain why, in many cases, we're using today algorithms that have been invented decades ago. Right, so if we think of many of the algorithms that we are using today, many of them have been invented pre-computational era, and this is something I think quite surprising for me. Why is it that AI cannot essentially discover these new algorithms, something that is much more efficient than what we have considered prior to the computation era? So more precisely, I'd like to talk about two works. The first one is we'll be studying a fundamental use case. So the use case of matrix multiplication, how we can take this fundamental problem of matrix multiplication and then convert it into a game, and then essentially have an agent that solves this game efficiently. And then we'll kind of zoom out completely from this particular use case and say, okay, like how can I discover new algorithms for completely different problems? Because as we'll see in number one here, we'll design things that are specific to matrix multiplication. In particular, we'll be using foundation models, large language models for the second part. Okay, so let's jump into it. I don't think I need to motivate why matrix multiplication is important for this audience, but it sits at the core really of many problems, from solving linear systems to simulation to neural network training and so on and so forth. So that's the kind of root node problem I was talking about, that if you're able to essentially unlock it, then it will have huge implications. So matrix multiplication, again, like I'm sure everyone is aware what matrix multiplication is about, but let me just put the notations. So this is essentially the operation of matrix multiplication for 2x2 matrices. So you have a 2x2 matrices, so 2x2, a grid of size 2x2. And these are the operations that we would use, or that we are all taught in high school or college on how to do matrix multiplication, right? And it was thought that this was the best algorithm to do matrix multiplication for a very long time, until what happened in 1969, some sort of like very surprising thing happened. where a German mathematician showed that you can do better than that, right? How do you do better than that? This is this weird algorithm here, right? Where you take some of the entries of A, and then you multiply them by some of the entries of B, and so on and so forth. You distribute them in this even weirder way, and then you get the right result. So it's very easy. Like, you can take this algorithm and do the math yourself, and you'll be able to see clearly that this is a correct algorithm, right? But it's really hard to come up with this, right? So I actually kind of invite you to take a blank piece of paper and say, okay, like, I want to multiply these 2 by 2 matrices with 7 scalar multiplications as opposed to 8, right? It's really hard to come up with that. Volker Strassen came up with it, and it was really a big result. Now, the first time I saw this, I mean, it's not very hard to see why machines could probably be better at that than us, right? So how do we best take matrices from the first matrix, and then matrices, entries from the first matrix and the second matrix, and how to combine them and so on. Why is this a big result? Because you can apply this algorithm recursively. So this algorithm is not specific to 2 by 2 matrices. You can really apply this recursively, and therefore get an algorithm of complexity n to the power log base 2 of 7, which is n, which is better than the n cube algorithm that one would typically use. Okay. So, in order to take this step of take this problem of matrix multiplication and then convert it into a machine learning problem, we need to slightly change the language. Okay. So I'll tell you a little bit how we can essentially formalize this as a game. So the first operation, the first thing we need to introduce is the matrix multiplication tensor. So just like linear operations, we can represent them as matrices. Bilinear operations, and matrix multiplication is one bilinear operation, we can represent them as tensors. Okay, so there is what's called the matrix multiplication tensor, which represents the operation of multiplying matrices. Okay, so it's independent of the matrices that you want to multiply. It's just the operation of multiplying matrices is captured by this matrix multiplication tensor, which is of size n squared by n squared by n squared. So more precisely, it's a tensor of, here, for example, for 2 by 2 matrix multiplication, it's a tensor of size 4 by 4 by 4. And it has 8 ones, and the rest is zeros. And the place where you put the ones correspond precisely to where do you read the entries and where do you write them. Okay, so that's, again, the operation of multiplying arbitrary matrices that is captured with this tensor here. Okay, so that's the idea of the matrix multiplication tensor. And then now that we can characterize what is the operation of multiplying matrices with a concise object, this matrix multiplication tensor, how can we express algorithms in this new tensorial language? Well, algorithms, it turns out that algorithms are just a decomposition of this tensor. Okay, so a low rank decomposition of this tensor gives you more and more efficient algorithms. Okay, so you have this tensor, this 4 by 4 by 4 tensor, for example, and you would like to find a low rank decomposition of this tensor. So a low rank decomposition of a tensor is just an extension of what we all know as a low rank matrix decomposition, where you have three factors, UQ, VQ, and WQ, as opposed to just UQ and VQ transpose. And here what you have is the tensor product. Okay, so it's not very hard to see why this gives you automatically an algorithm to multiply matrices, but essentially that's exactly what we want to do. We want to decompose this matrix multiplication tensor into the smallest number of rank 1, a sum of rank 1 tensors. Okay, so the problem, we took this problem of finding new algorithms for matrix multiplication, and then we're converted it into a problem of we have a tensor, and we want to decompose it into a sum of rank 1 tensors in the most efficient way. Like, as surprising as it might sound, even for tensors of size 9 by 9 by 9, we don't even know what the rank of these tensors are, right? So there is no efficient algorithm to compute the rank of tensors, unlike there is efficient algorithms to compute the rank of matrices. Okay, so, and this is precisely where we will be using AI. We'll be using AI to compute the rank of tensors, therefore getting algorithms to do matrix multiplication. So we'll be using AI to find low rank decomposition of this particular matrix multiplication tensor. Okay, so how do we frame it as a game? We have a board, right? So we don't have a 2D board, we have a 3D board now. The board corresponds to this matrix multiplication tensor here. And then what the player can do at each step is to essentially subtract a rank 1 tensor from this board, okay? That's the action space. That's what the player can do. So it's a single player game. And then you're going to iterate. Now, you've won, the player won, if you reach the 0 tensor at the very end. Okay? If you reach the 0 tensor at the very end, then what it means is that you found a low-rank decomposition of the tensor, and therefore you found an algorithm to multiply arbitrary matrices. Okay? Now, obviously, you don't want to find the 0 tensor in any way. You want to find it in the most efficient way, right? So that's why you have, we're giving a negative reward at each step. And then at the very end, you have a reward that corresponds to essentially the penalty if you don't reach the 0 tensor. Now, the game is defined as follows. There are many difficulties, as I said before. It's a huge action space. Actually, the number of rank 1 tensors is infinite, right? So at each step, you need to choose a rank 1 tensor out of an infinite number of actions. There's no training data, unlike chess and Go. You don't have available training data of decompositions, good decompositions of tensors. It's just this one tensor that you care about, right? So it's not very common in machine learning where you care about this one target that you want to, this one target or this one theorem, this one tensor, this one knot that you'd like to unknot. And if you do it, then you kind of like hit the jackpot. Otherwise, you're not interested. But this is very common in science, where you don't care about an IID. You don't have an IID setting, but you have an out of distribution setting where you have this one data point that you really care about. And then there is multiple symmetries, of course. Like if you take a tensor and then you permute, for example, some of the slices, like all the slices together, then you get the same rank. So maybe a small comparison with respect to Go. What we see when we compare essentially this game compared to Go is that the main difficulty here comes from the action space, right? Again, as I said here, the action space is infinite, but even if we discretize it, even if we say that each factor, let's say, has either like -1, 0, 1, or something like that, then the action space becomes combinatorially large, as opposed to Go here, where you have just the action space corresponds to 19 by 19, which is the size of the board, plus 1. 362. Yes?
The 3D tensor is binary?
Yes.
So why do we allow the rank 1 to be real value? Can't you restrict it by?
You mean the factors, right? No, so you need to consider also negative values, because even if you look at Strassen's algorithm here, you see there are negative signs here, right? And these correspond to the factors, right? So what will happen is that if you actually kind of unroll Strassen's algorithm, there will be cancellations between different terms that will let you get this 7 rank instead of 8, right? So if you only consider 0 and 1, you will not be able to do these cancellations, and therefore you won't be able to get the low rank decomposition. So the tensor is binary, but the factors can be anything, just like a matrix, right? So even if you have a matrix that is binary, a decomposition, a rank decomposition, can have any factors. Okay, so the approach that we'll be using is essentially relying on Monte Carlo tree search, right? So Monte Carlo tree search is this approach where at each step of the game, you're going to do thousands of simulations, right? Using these thousands of simulations, you're going to gather data, right, about what is the most interesting, what looks like the most interesting next step to take. So you're going to choose the actions based on how interesting they look like, or how interesting they, like the value function and the policy looks like, but also how much exploration did I previously do of this particular node, right? So it's a combination of these two things. I won't go into the details of the technicalities, but that's essentially the underlying idea. So of course, like this action space, the tree is huge, right? So we need to have some sort of guiding strategy in order to tell us which one looks the most promising and which ones are not promising. And this is precisely what the neural network would be able to tell you. And combining this Monte Carlo tree search with a neural network that tells you which one is the most promising is precisely the basis of AlphaZero, right? Which has been used to play games like chess and Go and so on. And so the underlying idea of AlphaZero is essentially that you have actors, right? Many actors that are playing in parallel. So think of many machines playing this game again and again, right? Initially playing really bad this game. But that's fine in the beginning, that's fine. So you're going to save all these games, and then you're going to send them to the learner. Okay, the learner has the neural network, and then what the learner is going to do, the neural network, is to essentially try to mimic as much as possible the games that have been sent to it by the actors. Your goal is essentially to predict what was the next move that was selected by the actors. Okay, now you update, you train your neural network a little bit on this data, and then you send it back to the actors. Now, in the next step, you're not going to do a kind of a random Monte Carlo tree search as you've done in the previous iteration, but you're going to consider this neural network as a baseline, and then you're going to try to improve over it, right? So you're going to use it as a guidance strategy, but you're going to do exploration over it in order to improve over the policy that is provided by this neural network. So you can think of this Monte Carlo tree search as a policy improvement operator, right? So that's essentially the high-level idea of AlphaZero. Now, in order to solve the challenges that I talked about, we obviously need a few, like many ingredients on top of this vanilla AlphaZero strategy. And I'm going to just select a few of the ingredients and tell you a little bit about some of the important components in order to solve this problem. So the first one is using synthetic data, right? So we know that we do have a source of data, which is this, which are these self-play games, or these games that have been played by the actors, but that's usually not enough. So obviously we don't have also like tensors and tensor decompositions that are available. So instead, what we can do is to rely on synthetic data. So tensor decomposition and many problems are what I call one-way hard problems. So getting decompositions from tensor is hard, but the opposite is really easy, right? So what you can do is to start from a random decomposition, and then you construct the tensor. So you have a tensor and rank decomposition pair, and then you can use this as a supervised example that you can train your network on in the beginning. Okay. Now you can incorporate symmetries in your training examples, but obviously the issue at the end of the day is that the distribution of synthetic data is very far from the distribution of the tensor that you actually care about, and that's usually the case. Now, even if that's the case, we saw that this was super helpful, especially at the beginning of training. The second ingredient I'd like to talk about is this idea that you care about just one target, right? That you care about decomposing this one matrix multiplication target, which is very far from machine learning setups, right? So one way to kind of get this distribution of tensors that you actually care about is to essentially use some sort of diversification operation. So here, the diversification operation is just a change of basis, right? So you can apply a random change of basis to this matrix multiplication tensor, and it's going to conserve its rank. But what will happen, essentially, like in a very hand-wavy way, is that these matrix multiplication tensors will get you closer to the training distribution, the random training distribution that you created. Okay, so it will be much more like a machine learning problem than it initially was. The third and last ingredient I'd like to quickly go over is to train a generalist agent rather than several experts. So initially in the project, let's say we were very focused on getting, let's say, for example, an algorithm to multiply 4x4 matrices in a certain ring, right? If you tackle only this problem by itself and you don't tackle many problems at once, what will happen is that you will overfit to this particular use case. And it's really hard then to do exploration around it. So instead, what we noted to be a very effective strategy is to consider different sizes. So the 2x2 size, for example, to rediscover Strassen's algorithm, but also to 2x2 times 2x3, and all the sizes essentially. up to a certain point, as well as different rings, right? Trying to find matrix multiplication algorithms in different rings. A very interesting transfer happens between targets that we didn't think transfer would happen in, right? So you could, for example, have a transfer between these two things, and mathematically there doesn't seem to be quite a lot in common. So the techniques seem to be transferred. So there, for example, is a relation, a mathematical relation between 2x2 matrix multiplication and 4x4 matrix multiplication, because you can get 4x4 matrix multiplication by applying twice 2x2 matrix multiplication recursively, right? So there is a mathematical relationship here. But what we notice is that there is also positive transfer happening between targets that we thought weren't related in any way. Okay, so the overall system therefore looks something like that. So you have this tensor, you apply a random change of basis, you do this this Monte Carlo tree search, you select a certain action, and then you subtract this factor, and then you move on and so on. You store this gain, you send it to the learner, and then again, like you have a mixed bucket of gains that are obtained from the actors, and then from these synthetic demonstrations that you feed into the network. I wouldn't go in detail about the architecture of the neural network, but it was kind of important also to consider some symmetries related to the problem in this neural network. And then you update your model, and then you send it to the actor, and so on and so forth. Okay, so that's the loop where you start really from sort of scratch, and then you get better and better agents at decomposing this tensor. So so as I said, we train this on many different agents, on many different targets. So from 2x2 to 2x2 times 2x2 matrix multiplication to 5x5 times 5x5. But again, remember that any of these algorithms, you can use them recursively. So you can actually apply them for any matrix size. So there is, because it's a very well-known problem, there is a tabulation of what's the best algorithm to do this kind of matrix multiplication. So for example, for Strassen, this is 7, right? The best algorithm to do 2x2 matrix multiplication is Strassen's breakthrough. And then the question is whether we can go beyond that, right? So you train your agent in the beginning, it rediscovers Strassen's in a matter of minutes. And then you continue, it kind of like rediscovers all the existing algorithms until a point where you actually go beyond existing algorithms. So for example, for 3x4 times 4x5 matrix multiplication, you get 47 as opposed to 48. And then you continue training, and here, for example, this one was of particular interest because the best way of doing 4x4 matrix multiplication was deemed to be 49, like applying Strassen twice, 7 times 7. But we've shown here that you can actually do better than that in particular rings. Okay, so for example, here in Z2. What does the algorithm look like? This is what it looks like, right? So again, an algorithm that is very hard to come up with, but relatively easy to check, right? So you can just do the math, and then you kind of like realize that this algorithm is actually correct to do 4x4 matrix multiplication. Okay, so that's what an algorithm looks like. So I want to take some time now to kind of like do a small wrap up of what we've talked about so far. So what we have so far is this new verifiable algorithms for matrix multiplication that outperform existing algorithms. And we do this by framing the problem as a game. But as you've noted, we like the way we framed the game, the way even we've set up the architecture is quite specific to the problem of matrix multiplication. So what if now I want to use, what if I want to discover new algorithms for bin packing, let's say, for vehicle routing, for maximum independent set? What should I do, right? Do I need to do the same kind of thinking and framing the problem precisely for that? Essentially tailor the formulation precisely for this problem. So this is when we started thinking, okay, how can we use foundation models? So you can think of these large language models and foundation models as a compression of the whole human knowledge into one model, right? So they certainly know a lot about matrix multiplication. They certainly know a lot about maximum independent set and so on, right? So how can we leverage those? So the first thing we tried is very dumb. We just ask it, right? So we can ask it, can you find a fast algorithm to do matrix multiplication and faster, let's say, than Strassen's algorithm? Unfortunately, what you will get is either of two things. You'll just get a copy paste from Stack Overflow or something or even worse, you'll get some algorithm that doesn't even make sense, is not correct, essentially. And in both cases are pretty bad, right? But still, like, how can we use these large language models? Perhaps there is a smarter ways of using these large language models in order to discover these new algorithms. And so the idea was really simple. The idea is to try to combine the creativity of a large language model with an evaluator that guardrails it against hallucinations. Okay, so you take the sort of creativity of a large language model and then you combine it with an evaluator. Now, we're fortunate that in mathematics and computer science, many problems are easy to verify but hard to solve. So what this means is that you can, like if you give me a candidate solution, it's really easy for me to check if this candidate solution is right or wrong and even to score it. Just like the tensor decomposition problem we've seen here. If you give me a particular tensor decomposition, I can just do the sum and see that whether this sum really sums up to the tensor. But coming up with the tensor decomposition is really hard. If you think of the maximum independent set, if you think of traveling salesman problem, they're all the same. They all, essentially, this applies to all of them. Essentially, like this is the complexity class NP, okay? So what we want to do here is to take fun search, or like to develop a technique which we call fun search, that takes as input this evaluation function, and then it outputs the solve function. That's kind of like our desiderata. Okay, so the way we do this is very simple. We start from essentially a trivial algorithm. Let's say, for example, to do tensor decomposition, as we've talked about before. You start from a trivial algorithm, and then you ask the large language model 100 times to improve over that, right? 95% of the time, it's going to be garbage. But 5% of the time, it's actually not going to be so bad. It's not going to kind of like give you the new algorithm that you cared about, but it's going to be maybe going in that direction, okay? So if you have a way to essentially tell which 5% are the good ones from the 95%, then you can essentially build on top of those until you arrive to the new algorithm that you really care about. Okay, so what we do is essentially a genetic algorithm or an evolutionary algorithm on top of a large language model. The large language model provides the mutations, right? And then we have the genetic approach, genetic algorithm approach that is taking the functions that have been generated by the large language model and building on top of them until you reach the functions that achieve a high score. So very simple in principle. Let's see how it works. So we applied this to a problem, the maximum independent set problem, which is an NP-hard problem where you're given a graph, and then the question is, what is the maximum number of nodes in this graph such that there is no two nodes that are connected, okay? Now, we don't want just to solve the problem in all generality, this largest independent set problem in all generality, but rather we want to focus on a distribution of graphs that really, for which things really matter, right? So we focused on a specific distribution of graphs that have a high mathematical significance, to the extent that one of the famous mathematicians says that this is perhaps his favorite open question, okay? And the reason why this is a particularly important graph distribution is that it's related to, or it's a reformulation of what's called the cap set problem, which is essentially that you're given a grid in 3 to the n, and then you're working in the group of the cyclic group of order 3, and you want to find the largest number of points such that there is no 3 points that are that lie on a line. Okay, so for n is equal to 2 for the plane, the maximum number of points you can choose out of those 9 is 4, because if you choose any other point, then 3 will lie on the line. Okay, so this independent set problem is just a reformulation of this combinatorial problem. So if you apply this fun search approach, this functional search approach, what you get for n is equal to 2 is 4. That's cool. That's easy. And then for 3, you get, again, the best previous construction. And then when you go to, like, notice how the graphs here get larger and larger. And then at some point, you essentially, again, go beyond the best constructions that have been considered by mathematicians. And because the search space is so large, previous human approaches or computer constructions weren't able to essentially go to large constructions like that. You can also improve essentially the asymptotics using this approach. But what's the most interesting beyond the numbers, I think, is that this is not the output of fun search. This is the output of fun search, right? So fun search gives you how you construct this large independent set. It doesn't give you the independent set. It gives you a way to construct this large independent set. So ask a mathematician to like which one he prefers, or even us, like which one we prefer between these two. And obviously this is the one, because we know precisely how to construct. This is very hard to essentially analyze and understand, right? So I think the fact that you're able to generate a program that generates the largest independent set is, I think, a super interesting, like from an interpretability and understanding point of view, is very valuable. So to our knowledge, this kind of discovery was the first time an LLM was used to discover a new result. So it's a provably new piece of verifiably true knowledge about a relevant scientific problem, but it's also a new way to do computation. So we use, we do a search in the space of functions. We really try to discover understanding rather than just facts. We don't want just to get the largest independent set. We want what is the program that generated this largest independent set. And the interesting thing, for example, is our collaborator, Jordan Ellenberg. He essentially was looking at these functions, and he was so excited about them that essentially he learned a few stuff. And given the fact that he's kind of like been in this problem for over 20 years, I think this is quite interesting. Yes?
Using this approach, can we know when it will not get something new and better?
When it will not? I mean, if it's, I mean, you can execute this, and then if it gives you an independent set that is smaller than what's known, then this is, you know, that it doesn't give you a better approach, right?
So my question is, the program that you showed is a successful one.
Yes.
Like you go and verify and check if this is the better than the existing one or not.
Yeah, I mean, you just execute it. This program returns exactly the independent set.
But this is by luck, or can we actually say that if you use functions this number of times, you are guaranteed to get something?
Oh no, there is no guarantees. I mean, no, there is. So whenever you have a program, you can run it, and then you can check that the independent set is larger than previously known. But there is no guarantee on the optimization, on the evolutionary approach itself, that it will give you a better result.
Since you cannot systematically to solve some, I don't know, the coloring problem, some other problems in class theory or something. So that my question was alluding to that fact. So what kind of questions we expect to solve using this kind of approach? So it's very good that we solved as a concept.
Yeah.
Can we know which we cannot solve or which we can solve?
So yeah, there are some problems that there is no way this can solve it. It's problems, for example, where you don't have this intermediate scores, right? So this kind of problem is an optimization problem, essentially, where you can score the different programs. If you have just a problem that is binary, either you're successful or you're not successful, this approach will not work, right? So yes.
Maybe I'm overlooking something, but how do you know that this function will work for all n? Like that's this sets for all n.
So this works, like this returns actually a 512 cap set for 8, n is equal to 8 only.
It doesn't necessarily work.
No, no. Okay, so what's I think it's something I've been thinking quite a bit about. And I'm really surprised that this approach works, I have to say. Like in the beginning, I thought that this wouldn't work. And there is an underlying theoretical question, I think, that is quite interesting, is that why is it that searching in the function space working so well, right? So it's not clear, right? Because you're doing a search in the space of programs that generate the result. Why not just do the search in the space of solutions itself? And so maybe just an informal answer is perhaps that because the most problems we care about are structured, the solutions tend to have a small Kolmogorov complexity. So the Kolmogorov complexity is this of a string is just the length of the shortest computer program that outputs the string. So for example, the Kolmogorov complexity of this string here is smaller than the Kolmogorov complexity of a random string. And similarly, the Kolmogorov complexity of a random image is way bigger than the Kolmogorov complexity of this fractal that I've shown on the right here, right? So what we're having here with fun search is an implicit prior that encourages solutions with a concise functional description, okay? And so we think that perhaps by searching in the program space, we're implicitly looking for objects with small Kolmogorov complexity, and therefore we're able to scale to larger ends, essentially, okay? So it's more efficient if we do the search in the space of programs than doing it in the space of solutions, because the problems we're considering are structured, and therefore the solutions tend to have a small Kolmogorov complexity. But it's still like a theoretical question. I think it's an interesting one to study. Okay, so beyond this maximum independent set, how can we use this in practice, right? So we said, okay, let's consider a practical problem, which is that of online bin packing. So you have, and in this case, we want to discover new heuristics for this problem. So you're given a fixed collection of bins, and you have a stream of incoming items, and then you want to place each item so as to minimize the number of bins that is used, okay? So there are lots of heuristics around this problem. This problem is central to job scheduling, for example, and other problems in logistics. And so you can try out different heuristics, but then you can also evolve heuristics, right? Just with fun search as we described here. And it turns out that with fun search, you're able to essentially find algo or heuristics that improve over existing heuristics like best fit and first fit on different benchmarks. So I think going forward, it's a very interesting way of discovering heuristics that are often quite difficult and painful to find for this kind of hard problems. So as I said, fun search is not useful in all cases, but I think it has some conditions for which it can be quite useful. The first one is that you have an efficient evaluator that is available, right? The second one is that you need to have a smooth scoring feedback. As I just said, you cannot just have a function, a problem that is 0 or 1, because you will not be able to do this evolutionary procedure. And then a third point here is that it's good to have prior information about the problem, right? So it's good to not start from scratch, right? So what we considered, for example, in the CAPSET problem is a skeleton of a greedy algorithm, right? So you kind of put in the prompt that you want a greedy algorithm, or you put the for loop associated to a greedy algorithm, but what you're missing is the priority function. Priority function is the function that essentially sorts in which defines the order at which you'll be visiting the elements. Okay, so that's the most important thing, obviously, in a greedy algorithm. So you're putting the greedy structure, but you're letting the large language model and the fun search here find the priority function. Okay, in this way, it's better, and the LLM finds it more efficient to just find the priority function than to kind of reinvent the wheel of a greedy algorithm. Okay, so I arrived at the end of my talk, so just maybe let me give some takeaway messages. The first one is that pairing an LLM with an evaluator I think gets surprisingly good results. At least it was really surprising for me. But I don't think we should overfit to thinking that the large language model does have a deep understanding about the CAPSET problem, or about the bin packing problem, or about the different problems. So what we're doing is essentially to use the large language model to get good mutations, right, in the space of syntactically correct programs. it's not that it finds kind of like amazing ideas in one shot, right? I think the idea of combining this incremental improvement with this random sampling is very interesting. There is this theoretical question which I alluded to at the end. When is it more interesting to solve combinatorial problems in the space of solutions versus in the space of programs that generate those solutions? But yeah, there is lots of remaining open questions in the field, and I think it's a very exciting time to be working in this field. Thank you very much.